Hi everyone, welcome to another video. In today's video we're going to be talking about how to do a one-way analysis of variance in R. As with all of these how-to videos, we're going to be assuming that you understand the statistical calculations and the underlying theory behind this test, and that you understand some fundamentals of R, such as how to import data and basic data manipulation functions. If any of those things are unclear to you, I have other videos on this channel that you can check out to either learn the statistical foundations or things about data manipulation. But this video is really intended to be more of a refresher on how to do these things in R, or a very quick introduction to how you can use some of these different functions for analysis specifically. Also, as a reminder, in the video description I'll have a link to the script file we're using, so you can follow that to my GitHub repository and then follow along with the R code that we'll be using today. Okay, so over here now in RStudio, we're going to open up the same libraries that we usually do. The additional library we'll use today is this EZ library. The EZ library is an analysis library that has a lot of really helpful functions for factorial analysis. And that is, factorial being when we're working with categorical factors as our independent variables. So I'll show you how to do analysis of variance using a lot of different tools. We're going to start with doing it with the general linear model, and then we'll also use the EZANOVA function from the EZ library. If you're transitioning into R from something like SPSS, it's going to give you an output and information that probably feels a little more comfortable and a little more familiar to you. So both of these ways will work, and we're going to try to cover them both today. But first, let's go ahead and open those libraries. We're going to download our data from the web, and we're going to start with the example that we used in the previous two how-to videos on how to do a one-sample t-test and a two-sample t-test, where we have this hypothetical study where students were randomly assigned to either take a SAT prep course or not take an SAT prep course, and then we recorded their scores on the SAT math course, or sorry, on the SAT math test. So first, if we want to actually do this analysis of variance using the general linear model, and as a reminder, everything is a linear model, right? So oftentimes, especially in introductory stats classes, regression and ANOVA are taught separately. But factorial ANOVA is really just a special case of regression where we're going to code a categorical predictor in a certain way. But we can still use an SAT score as our outcome, look at it as a function of whether you were assigned the course or not, and then conduct an analysis of variance from that model. So a good way to do that is using the capital A ANOVA function from the car package. Base R also has a uncapitalized little a ANOVA function, but the reason why I like the capital A ANOVA function is because of this argument right here. The capital A ANOVA function allows us to be explicit about the type of sum of squared errors calculation that we're going to be using. And for all of these examples today, we're going to be using the type 3 sums of squared errors. If you don't remember the difference between type 1, type 2, and type 3 sums of squared errors, please check out my other videos on types of sums of squared errors. So once we have that linear model built, though, we can pass the model object into the ANOVA function, and you'll see it returns to us an ANOVA table using type 3 tests. It gives us the sums of squared errors explained by the intercept, by our group variable, and then in the residuals, the degrees of freedom that go with each one. It skips over the calculation of the mean squared error to give us the F values. So the F value for the intercept is quite large. And the F value for the effective group is also, pretty good size, an F of 4.39. But as we saw with the t-test example, it is not less than 0.05. So this would fail to reach statistical significance, as many people would define it using like Nyman-Pearson hypothesis testing. So, this is still relatively interesting, right? And we'll look at some confidence intervals around those data in a minute. But at the moment, it is not does not fall in that less than 5% under the null. So we would not decide to reject the null in this scenario if we wanted to maintain that type 1 error rate of 5%. We can get a complementary look at this if we use the summary function. Now, the summary function does not return an ANOVA table, and it does not return F statistics. Instead, it's going to return the individual coefficients from our model, the standard error for each of those coefficients, and then the t-value. So you can see, again, we have an intercept, which is statistically different from 0, agreeing with our analysis of variance. And then we have this variable of group no course, which has a value of negative 28 for the slope. It has a t-value of negative 2.096, and it has a p-value of 0.505, identical to the value we saw for the analysis of variance. Because again, these are asking complementary questions. We are asking about the difference between groups, in this case, with the t-value. In the ANOVA value, we're asking about the variance explained by what group you are in with an f-test, but those are both not less than 5% of what we would expect, assuming that the null hypothesis of zero difference between groups was true, or the null hypothesis of zero variance actually explained is true. If we wanted to do this then using the EZANOVA function from the EZ package, we have that on lines 22 through 29. We can set where the data are coming from, what the dependent variable is. We need to specify what the grouping variable is, even though in this case we do not have any within subject factors. We then specify what the between subjects variable is, and then we specify the type of sums of squares that we want to use. Now, the analysis of variance output from the EZANOVA function is a little bit different, but you can see that it all agrees, right? We get this effective group. It gives us the numerator and the denominator degrees of freedom, the f value, the p-value that corresponds to that, and then it also will add a generalized effect size measure of 0.196. And without getting into too much detail about what the generalized effect size measure is, I'll include a link to the EZANOVA package so you can look at their documentation to see how they calculate that. But this is conceptually similar to a partial eta squared that you might be familiar with from other ANOVA calculations and classes. One nice thing about the EZANOVA package is it's going to include things like Levene's test for homogeneity of variance. If we had a within subject factor here, it would also include things like a test for sphericity. But because we only have between subjects factors, it's focusing on the homogeneity of variance assumption. And although I wouldn't always recommend statistical testing as the best way of dealing with homogeneity of variance, you can see that we have a very large p-value here. So there's very similar variances between our two groups, which is also reflected over here in the box plot, right? Kind of the range of the data for the course group is very similar to the range of the data for the no course group. So those two variances are not statistically different from each other. If we wanted a slightly different way of looking at this, we can do a little bit of math to get the means of each of our data sets. So that's what I'm doing here. I'm just calculating the mean, the standard deviation, the sample size, the standard error, and then the upper and lower limits for the 95% confidence interval for both the course group and for the no course group. And then armed with those mean data, I can now generate a plot using ggplot, where I'm going to plot each mean, and I'm going to plot the 95% confidence interval in each group. So this is conceptually different from what we did in the previous example when we looked at a two-sample t-test. In that script, we actually calculated the difference between groups and then calculated the 95% confidence interval of the difference. In this one, we're calculating the mean in each group and then calculating the 95% confidence interval of that mean. So those are conceptually different things. If we only had, two groups, I would usually try to do what we did in the t-test example and show the mean difference and the confidence interval for the mean difference, because that's what's ultimately going to correspond to the statistical test we're running. This is more effective as sort of a descriptive statistic about how much we, what mean we observed here, and then what plausible values of this mean are in the population. The reason why I'm doing this rather than plotting the difference, though, is that in our next example, we're now going to have a categorical factor with 3 levels, and then it's going to be a lot more differences that we would have to plot. So sometimes you want to plot differences in their confidence intervals. Other times you'll want to plot means and their confidence intervals. There's not one that's right or wrong. It really just depends on your research question and what you're trying to convey to your audience. So looking at this next example, we're going to import the data. It's called DAT2. And DAT2 actually, rather than looking at the head of this, let me actually just print all of these data to the screen because it's not too much. You can see that these data are VO2 max and runtime data from 3 different groups of collegiate athletes. And again, this is data that are loosely based on a real example, but the data themselves are fictitious. So you can see our subject ID numbers in the first column, the VO2 max for that particular athlete in the second column, the time it took them to run an 800 meter sprint, I believe, and then whether they were a Nordic skier, a soccer player, or a recreational control athlete. And again, as before, we have two different ways of approaching this that are equally valid. The first one, we'll build a linear model where we're looking at the VO2 max as a function of what group you're in. And then we can do an analysis of variance for that linear model. And you can see that for our group effect, with 2 and 18 degrees of freedom, the F value is 37.56. And our p-value is very small. So this is suggesting that group is explaining way more variance than we would expect if the null hypothesis were true. And therefore, we're going to reject the null hypothesis in this situation and instead assume that there is some systematic differences between these groups. Now, we can also get more information if we get a summary of this linear model, which I have shown here. And this is, the same conceptually as the summary output for a linear model we got before. But the difference is that now we have not only an intercept, but we have two slopes. And depending on how you have coded your categorical factor, that's going to change the interpretation of these slopes. So in our case, the recreational athletes are getting coded as the reference group. So this is actually the mean VO2 max. This intercept is the mean VO2 max of the athletes in the recreational group. This slope tells us about the difference between the Nordic athletes and the recreational athletes. And this slope tells us about the difference between the soccer athletes and the recreational athletes. And then we have t-tests both for that intercept and for the two sets of differences. So this summary output can be a really nice complement to what we get from the ANOVA. The ANOVA output is going to give us the omnibus F for all of our groups as a set. And does the variable group explain more variability than we would expect under the null hypothesis? And it did. And that gives us justification to really delve further into these individual contrasts. And we can see now not only are there differences between groups, but more specifically, the Nordic athletes have a statistically higher VO2 max than the recreational athletes, and the soccer athletes have a statistically higher VO2 max than the recreational athletes. That we feel pretty comfortable generalizing back to the population because those are statistically significant differences. Again, we can do the same thing using the EZANOVA function. So we're going to refer to our new data set. The dependent variable is that VO2 column. Our subject identifier is subject ID. We have no within subject variables in this example. We have the between subject factor of groups, and we want to use the type 3 sums of squared errors. And if we do that, you can see that we're going to get our omnibus F test here with 2 and 18 degrees of freedom. The F is 37.56, and again, a very small p-value with a large generalized effect size. So this would be a statistically significant omnibus F test, giving us a good justification to delve into individual post-hoc comparisons. I'm not actually going to take the time to do that here, but I will put a link to my other video on sort of strategies and approaches for doing post-hoc testing in the video description. Finally, now we can actually look at these data in a plot. So we'll do a little bit of math, again, to get the means, the standard errors, and the confidence limits for each of those groups. And then, using ggplot, we can get a nice dot plot with error bars showing the mean and the 95% confidence interval for the control athletes, the mean and the 95% confidence interval for the Nordic athletes, and the mean and the 95% confidence interval for the soccer athletes. So this would be a pretty nice visualization, helping reinforce what we've seen from our omnibus F test, which is that there are differences between the groups overall, and what we've seen from the summary output of the linear model, which was that the Nordic athletes have statistically higher VO2 maxes than the controls, and the soccer athletes have statistically higher VO2 maxes than the controls. So hopefully that helps you with kind of understanding how to run a one-way analysis of variance in R and gives you some ideas for the types of visualizations you might want to do to convey those results to your readers.